All right, let's get into this explainer on a really fascinating and pretty unconventional theory about what holds our atmosphere together. It's an idea that challenges some things we think we know and throws a completely new variable into the mix to solve some very old puzzles. So here's our roadmap. We're going to start with a fundamental question about the air we breathe. Then we'll introduce this novel theory that's all about charge. After that, we'll see how the author applies it to nitrogen, oxygen, CO2, and even the atmospheres of other planets. First up, let's tackle a question that sounds incredibly simple, but according to the source material for this explainer, the common answer just doesn't really add up. Think about it. Oxygen gas is about 14% heavier than nitrogen gas. So over millions and millions of years, why doesn't gravity do its thing and sort them into layers? You'd expect the heavier oxygen to settle down here with us, right? Well, the textbook answer, like this one from Johns Hopkins, is basically that the particles are just moving too fast. They're zipping around at incredible speeds, constantly mixing everything up, so gravity never gets a chance to sort them.
But this is where the author of our source material steps in and says, hang on a second. They argue this explanation doesn't make sense. If you shake a jar of sand and pebbles, the shaking actually helps gravity separate them. The idea that just moving fast is enough to defeat gravity's sorting power is, in their opinion, just not good physics.
Okay, so if the "they move too fast" explanation is out, what's the alternative? This is where the source papers introduce a pretty radical new concept they call the unified field weight. So the core idea here is that a gas's behavior isn't just about its normal physical weight, the pull of gravity. The theory suggests there's another force at play, what the author calls a charge field, and an element's interaction with this field can actually add or, more importantly, subtract from its effective weight.
And here's the punchline of the whole theory. For a gas to just hang out in our atmosphere for billions of years, it can't just be floating. Its downward pull from gravity has to be almost perfectly canceled out by its interaction with this charge field. It has to be in a state of near-perfect balance.
Now let's circle back to our original mystery and see how this unified field weight idea is supposed to explain the perfect mixing of nitrogen and oxygen.
This is where the rubber really meets the road for the theory. The author uses ionization energy as a stand-in for this charge mass, and what they find is pretty wild. Oxygen is 14.3% heavier than nitrogen, but nitrogen has a charge property that is 14.5% stronger than oxygen's. It's like a cosmic tug-of-war, where the two opposing forces almost perfectly cancel each other out. And this is the central claim. Because these two forces are in such opposition, the net difference in their unified field weights is tiny, less than 0.2%. They effectively weigh the same in the atmosphere. And that, the author argues, is why our air is so incredibly stable.
Okay, so that seems to work for nitrogen and oxygen. But what about a gas we hear about all the time, carbon dioxide? Is it balanced?
Well, according to the author, the answer is a big fat nope. CO2 is way heavier, and its charge properties don't come anywhere close to making up for that extra gravitational pull. It's about 10% out of balance, which means it's fundamentally too heavy for Earth's atmosphere and is in a constant, slow process of falling back down.
This idea leads to a really staggering critique of mainstream models. The author claims they're off by 2,700%. Now, how on earth do you get a number that big? They argue that scientists measure all the CO2 produced at ground level from things like decaying plants, but then compare that number to concentrations measured high up in the atmosphere, a place where, according to this theory, much of that heavy ground-level gas never even reaches.
As you can imagine, this completely changes the picture of how long CO2 sticks around. The mainstream estimate is about 5 years, but the author's calculation gives an average of 122 years. The key argument is that for an unbalanced gas like CO2, its residence time isn't one simple number. It increases dramatically the higher up it gets. Now, to really put this theory to the test, the author does something brilliant. They expand the scope beyond Earth. They use this idea of a unified field balance as a potential key to unlock the secrets of our planetary neighbors' atmospheres. And this is where it gets really compelling. Remember how CO2 was supposedly 10% too heavy for Earth's gravity? Well, get this. Venus's gravity is almost exactly 10% weaker than Earth's. The theory predicts this is the perfect sweet spot to balance the CO2 molecule. And what's Venus's atmosphere made of? Oh yeah, 96.5% carbon dioxide. Coincidence? The author thinks not.
And this same logic gets applied all across the solar system. On Mars, the gravity is too weak, so gases like CO2 become too light and just get blown off into space. On Jupiter, the gravity is much, much stronger, which, according to this theory, is why it's perfectly balanced to hold on to lighter gases like methane and ammonia.
So the big takeaway from this entire explainer is that this theory proposes a brand new rule for how atmospheres get built. It's not just about gravity. It suggests a planet's gravity and this proposed charge field create a specific weight class, and only the gases that fit that profile perfectly get to stick around for the long haul.
And that leaves us with a really provocative final question. When one single, unconventional idea seems to elegantly connect a bunch of dots that seemed unrelated before, from why our air mixes to what Venus's atmosphere is made of, you have to wonder, what's the difference between a radical theory and a real paradigm shift? And what does it take for an idea like that to truly be heard?